Start.
Hello students. Yesterday we have discussed about the solubility and the types of solutions based on solubility. Okay, and the factors affecting solubility. What are the factors affecting the solubility? We have seen that it is the temperature, pressure, nature of solute and solvent. Okay, and also we have discussed about the solubility of the gases in the liquid and the factors affecting it. Okay, so briefly let me tell it. The factors affecting the solubility of a gas in the liquid are nothing but the nature of the gas, temperature and pressure. Okay, as the temperature increases, the solubility of the gas decreases, and as the pressure increases, the solubility increases. Okay, and the effect of solubility and the effect of pressure on the solubility of a gas was explained by Henry's law. And also we have seen the applications of Henry's law. Okay, and we have also discussed about Raoult's law. What is Raoult's law? Raoult's law, it states that the decrease in vapor pressure due to the addition of a non-volatile solute in the solution is because it is equal to the mole fraction of the solute. Okay, if we are dissolving more amount of the solute, the decrease in the vapor pressure would be more. Okay, we have discussed all these yesterday. Now let us go into the further part of the chapter. Okay, so the solutions whichever obey Raoult's law are called as ideal solutions. Okay, and the solutions which do not obey Raoult's law are called as non-ideal solutions. Okay, non-ideal solutions are also called as real solutions. So now let us see why is a solution behaving as an ideal solution and what is the reason why the solution is behaving as a non-ideal solution. Let us see. Okay, so ideal in the sense what? It is nothing but the expected vapor pressure. Okay, the expected vapor pressure would be equal to the theoretical vapor pressure we are obtaining after making the mixture. That is the solution. Okay, so let us see the definition over here. The forces of interaction in the solution are the same as in the pure components. That is, AB interactions are same as AA and BB interactions. So what are these? Let us see here. Suppose, let us take the solute as A, okay, and the solvent as B. So, whatever the substance we take, they will be having the intermolecular attractive forces. So, in the substance A itself, we are having A interactions, and in the substance B, we are having BB interactions. Okay. Now, I am preparing the solution by mixing A and B. Okay. So, after we mix A and B, the interactions are same as that of AA and BB. Okay. So, because these interactions are similar after mixing also, these solutions will be obeying the Raoult's law. Okay. So, we call such solutions as ideal solutions. Okay. And for these solutions, delta V mix. So what is delta V mix? Delta means it is the change. Okay. Change in the volume. So suppose if I am taking 30 ml of the solute and 70 ml of the solvent. So what would be the volume of the solution? It would be 30 plus 70, nothing but 100 ml. The final volume should be 100. Okay. And what is the initial volume? 30 plus 70. It should be also be 100. So what should be the change? 100 minus 100. Okay. Expected minus real value. So sometimes in real, what we are getting is actually 30 plus 70, we should get it as 100. But in reality, sometimes we are getting this value as more, or sometimes we get it as less. Sometimes we get it as equal. Okay. So if we are getting these expected values as same, we say that it is an ideal solution. And change in the volume would be 0. Okay. I hope it is clear. What is delta V mix? After we mix the solute and the solvent, okay, the change in the volume would be 0. Change in the volume would be 0. Okay, that is for the ideal solutions. And delta H mix. What is delta H? Delta H is nothing but it is the heat of solution. So what is heat of solution? Let us see here. Whenever we are mixing a solute in the solvent, okay, that means a solution is formed. Okay, so whenever a solution is formed, heat is either released or absorbed. Okay, so when the heat is released, what happens? The reaction vessel becomes hot. Okay, and sometimes the heat is absorbed. So whenever the heat is absorbed, the reaction vessel becomes cool. Okay, sometimes, so this is what we observe in the reality. Sometimes the heat is released, sometimes the heat is absorbed, and sometimes the temperature remains same after we are forming the solution. Okay, if there is no change in the temperature, we say that delta H mix is 0. Okay, so for the ideal solutions, delta V mixture is 0, delta H mix is 0. Okay, and see this one, PA. What is PA? PA is nothing but it is the vapor pressure of the component A. Okay, and PB is the vapor pressure of the component B in the solutions. Okay, P naught A, this is the vapor pressure of A in the pure state. P naught B, it is the vapor pressure of the B in the pure state. So after we are mixing these and we are forming the solution, okay, the values are like this. PA is equal to P naught A into XA. What is XA? XA is nothing but it is the mole fraction of A. Okay, XB is the mole fraction of B. So such type of solutions are called as ideal solutions. So what are ideal solutions? They obey Raoult's law. Delta H mix is 0. Delta V mix is 0. Okay. And examples are N-hexane. N-hexane means normal hexane and heptane. Whenever we are mixing N-hexane and heptane, it is behaving as an ideal solution. That means it obeys Raoult's law. Another type of solution which obeys Raoult's law is benzene and toluene. Okay. And another example is bromoethane and chloroethane. So these are the solutions which are obeying the Raoult's law. Okay. And hence, because they are obeying Raoult's law, we are calling them as ideal solutions. So next, let us see the other side of it. Okay. We said now. So all the solutions are not ideal. Okay. They are deviating from ideal behavior. Okay. So such solutions are called as non-ideal solutions. Okay. So in simple, we can say that non-ideal solutions are the solutions which do not obey Raoult's law. Okay. So similarly, same example we will take here. We are taking two substances, that is A and B. Okay. So here among the particles of A, we will be seeing AA interaction and BB interaction, the molecules. Okay. The molecular interactions would be there. Okay. AA, BB. Okay. before we are forming the solution, they are having these interactions. And these interactions, AA interactions, are not similar to the BB interactions. The interactions are different from one another. Okay. Now we are mixing these and forming the solution. So what happens? A and B are mixed. So we get the A plus B mixture. So when A plus B are mixed, again we will be seeing A and B interactions. Okay. So this A and B interactions, they can be more than AA or they can be more than BB. Okay. So what happens is they can be more, they can also be less. Okay. If the interactions are more, what happens? The molecules will tend to be in the solution form itself. Okay. The molecules will be tending to be in the solution form itself. Okay. Suppose after we are mixing A and B, the interaction is not much. So what happens? They do not want to be in the solution form. They go away from the solution form. That means they are going into the vapor phase. See, one common example. If we are having good friends, what do? We sit and keep on chat with them. We avoid our work. Yes or no? Because interactions are much. Okay, same thing here. What is happening is, if the interaction between the solute and the solvent molecules are much, they tend to be in the solution form itself. They do not go into the vapor phase. Whereas if the interactions between the solute and solvent are less, instead of being in the solution form, they tend to go into the vapor form. Okay. And for the non-ideal solutions, delta H mix, that is what? The heat of the solution is not zero. That means after we are mixing the solute and solvent, either the heat is absorbed or the heat is released. Okay. When we are saying that when the either heat is absorbed or released, means what? There is a change in the temperature. Okay. Heat is related with temperature, right? So when we are forming the solutions of non-ideal behavior, there is a change in the temperature. Okay. And for non-ideal solutions, delta V mix is also not equal to zero. Okay. Not equal to zero means what? There are again two probabilities. It can be greater than zero. It can be lesser than zero. Okay. So suppose you see here, I am taking 30 ml of the solute, 70 ml of the solvent. Okay. So final volume of the solution should be how much? It should be 100. Okay. But in reality, what is happening is, sometimes it can be more than 100. Sometimes it can be lesser than 100. Okay. This is practically what we see for the non-ideal solutions. Okay. When it is more than 100, the delta V mix would be greater than 0. Because suppose if it is 102, you think 102 ml it becomes. So what would be delta V mix? 102 minus 100. So it would be 2. Okay. Sometimes the volume gets decreased. Okay. So delta V mix would be lesser. Okay. So the examples of non-ideal behavior solutions are carbon disulfide and acetone. That means when we are mixing carbon disulfide and acetone, we are getting a non-ideal solution. Non-ideal solution means it does not obey Raoult's law. Okay. And another example is ethanol and acetone. Okay. When we mix these two solutions, or when we mix these two substances, okay, they form an non-ideal solution. Okay. You might have learned in the last year in your junior intermediate about hydrogen bonding. Okay. What happens is, ethanol molecules, Okay, they have intermolecular hydrogen bonding. Okay, once we are mixing acetone with the alcohol, ethanol, the hydrogen bonding will be broken. Okay, so they are behaving as non-ideal solution. So once the hydrogen bonding is broken, now they will be going into the vapor phase easily than to be in the solution phase. Okay, this is about ideal and non-ideal solutions. Okay. Yeah. Now we will see types of non-ideal solutions. Okay. Non-ideal solutions are further classified as negative deviation solutions and positive deviation solutions. Okay. So first let us see the negative deviation solutions. So what are these negative? Let us see here. The force of attraction increase by mixing. Okay. Okay, by mixing AB. So what happens? See here. Again, AA is the solute, BB is the solvent. Okay. When we are mixing A and B, we are getting AB mixture. So here the interaction between A and B is more. After we are mixing, the force of attraction increases. So what happens? This AB, they will be tending to be in the solution form itself. Okay, it is just like if you are meeting your friend, what happens? You keep on sit and chat with them. You will avoid your work. Same thing here. Here, because AB interactions are more, these are tending to be in the solution form itself rather than going into the vapor phase. Okay, so because they are not going into the vapor phase, what will happen? The vapor pressure will be lower than given by the Raoult's law. Okay, because the vapor pressure is lesser, okay, than given by the Raoult's law, we are telling it as a negative deviation. Okay, and for the solutions exhibiting negative deviation, delta H of the solution, that is heat of the solution, is negative. That means negative in the sense what? It is an exothermic solution. That means heat is released. So what do we understand from this? Heat is released. So after the solution is formed, okay, heat is released means their molecules are losing the energy. Because they are losing the energy, they are not capable to go into the vapor phase. Okay, you can understand in this way also. Because the heat is released, the energy of the molecules will decrease. Heat is nothing but it is an energy. Okay, energy is required for the molecules to go into the vapor phase. Because they are losing the energy, they will not go into the vapor phase. And because they are not going into the vapor phase, the vapor pressure would be lower than expected value. Okay, so because it is less, we are calling it as a negative deviation. Okay. Next thing what it is saying, temperature change when solution is formed. So it will increase. Yeah, temperature, because whenever the heat is released, the reaction vessel becomes hot. Okay. By that we can come to know. So an example is acetone and water. So whenever we are mixing acetone and water, it forms a solution of negative deviation. Okay. I hope it is clear. Next, let us go to the positive deviation solution. Okay. So here, what happens? The force of attraction decrease by mixing AA, BB. So see here, same thing. We are taking the solute A and solvent B. So A interactions are there and BB interactions are there. Now, once we are mixing A and B, the interaction would be AB. Okay. So the attractions are decreased. Okay. So instead of being in the solution form, they are going into the vapor phase. So similarly, suppose if you find your friend who doesn't talk to you much, so what do? Instead of wasting your time over talking, you'll do your work. Yes or no? Same thing here. When we are mixing A and B, here the attractive force are less. So instead of being in the solution phase, they are going into the vapor phase. Okay. So when these are going more into the vapor phase, so the vapor pressure as expected by Raoult's law is more. Okay. Actually, we are getting more vapor pressure than shown by Raoult's law. Okay. Than the expected one, we are getting real ones is more. Okay. So you see here, the vapor pressure will be higher than that given by Raoult's law. Okay. And delta H of the solution, that means heat of solution is positive. Okay. Heat of solution is positive means what? Here, the molecules are taking the energy from the surroundings. Okay. So whenever the molecules are taking energy from the surroundings, so what happens? Their energy increases. Yes or no? When they are increasing their energy, so they will move away. Okay. Once they are getting the energy, they are easily now going into the vapor phase. So because they are going easily into the vapor phase, the vapor pressure will be higher. Okay. And whenever the process is endothermic, endothermic means the heat is absorbed. Okay. We see that the reaction vessel becomes cool because surrounding heat is absorbed, no? So the reaction vessel becomes cool. Okay. And the temperature change when the solution is formed is it decreases. The temperature generally decreases. So an example over here is ethanol and hexane. Okay. Whenever we are mixing ethanol and hexane, we are getting a positive deviation solution. Okay. And that just now I said now, ethanol, you have learned in the last year that ethanol has intermolecular hydrogen bonding. Okay. Ethanol has intermolecular hydrogen bonding. So when you are mixing hexane in ethanol, so what happens? These hexane molecules will break this intermolecular hydrogen bonding. Okay. So because of the breakage of the intermolecular hydrogen bonds, now the ethane molecules, they will become free. Okay. Once they are getting freed, they are now easily going into the vapor phase. Okay. And for that reason, we are getting the positive deviation. Okay. Hope you have understood. Please read the textbook as well as go through the slides and as well please read the textbook. So now these are the graphs, okay, shown by non-ideal solutions. Okay. So see this one. For solution showing positive deviation from Raoult's law. Okay, positive deviation means what? Delta H is greater than 0. Delta V is greater than 0. Okay. And PS is vapor pressure of the solution is greater than P ideal. Ideal in the sense what? As expected by Raoult's law. Okay. So here these dotted lines, they represent the vapor pressures, okay, as expected by Raoult's law. And these red lines, they represent the vapor pressure that are obtained practically, okay. So just by seeing the diagram, you should be able to say, okay, see, these red lines are above the dotted lines. Above means what? They are having higher values. When will it be higher? Because it is exhibiting the positive deviation. Okay. Now, let us see the graph for the negative deviation. Okay. Same thing over here. The dotted lines are the expected vapor pressures because of Raoult's law. Okay. And these red lines are the theoretical, these are the practically obtained values of vapor pressure. Okay. And see, these red lines are below the dotted lines. Below means what? They are lesser. The values are lesser than expected values. In real, we are getting lesser vapor pressures. Okay. Why are we getting lesser vapor pressures? Because it is exhibiting negative deviation. Okay. Why is negative deviation? Because of more interactions between A and B. Okay. And for negative deviation solutions, delta H is less than 0, delta V is less than 0, and vapor pressure of the solution is lesser than the vapor pressure of ideal solution. That means as expected by the Raoult's law. Okay. Now let us see the limitations of Raoult's law. Okay. Limitations. Limitations means what? It is the drawbacks. Okay. So Raoult's law is applicable only to very dilute solutions. Okay. This is one thing. So Raoult's law, it has to be applied only for the dilute solutions. And it is, Raoult's law is applicable to the solutions containing non-volatile solute only. Okay. So whatever the solutions we are forming, the solute should be non-volatile. Only for such one it is applicable. That means it is not applicable to the volatile solutes. Okay. And Raoult's law is not applicable to the solutes which associate or dissociate in the particular solution. So what is dissociation and association? Let us see here. Suppose if we take sodium chloride. What is sodium chloride? It is the common salt. Okay. Its formula is NaCl. And we know that it is a polar compound. Okay. It is made up of Na plus and Cl minus ions. So when we are mixing this in the solvent, for example, we are forming a solution by dissolving this in the water. So what happens is it breaks into Na plus ions and Cl minus ions. So here it is dissociating. Okay. So for such type of solutions, it is not applicable. The solutes which dissociates, okay, it is not applicable. Okay. And associates. For example, if you take acetic acid, okay, acetic acid, when it is mixed in water, what happens is it exists as a dimer. That means two molecules will associate themselves because of hydrogen bonding and they appear as a single molecule. Okay. So such type of solutes which either associate or dissociate, for such type of solutes, Raoult's law is not applicable. Okay. This is about this is very, very important concept. You please all have to learn the Raoult's law, its limitations and deviations, positive deviation, negative deviation. This is very, very important for your competitive exams as well as for your intermediate public exams. Next, let us go through the another topic, that is azeotropic mixture and its types. So what are azeotropes? We will see here. Azeotropic mixture also we can call it as azeotrope. Okay. So an azeotropic mixture is nothing but it is the mixture of substances that has the same concentration of vapor and fluid phases. That means what? I have mixed the solute and solvent. Let the solute be A, solvent be B. Okay. So now what do I get? AB type of solution. Okay. The solution is AB type. Now, what happens is the interaction between A and B molecules is such that whenever they are going into the vapor phase, these two are going together. Okay. That means the interaction is much between A and B that they are either going to the vapor phase intact or they are tending to be in the solution intact. Okay. Yeah, in our common example, we can say, sometimes if our friendship is very much with one of the friend, what do? Wherever we go, we carry that friend. Yes or no? So same thing in the solutions also. In the azeotropic mixtures, what happens is the attractive forces between the solute and solvent would be such that they are having the same concentration in the vapor phase as well as same concentration in the fluid phase. Okay. So such type of mixtures are called as azeotropic mixtures. Okay. And one thing about those is because they are having the same compositions in the fluid phase as well as in the vapor phase, we cannot separate these components by fraction. This one, fractional distillation. Okay. You might have already learned in your previous classes what is fractional distillation. It is a technique to separate the components of a mixture by heating them, okay, till they reach their boiling points. So if a mixture forms an azeotropic mixture, what happens is, though we are heating them, the solute and the solvent will go into the vapor phase. Okay, that mixture is only called as azeotropic mixture. Okay. And we are having two types of azeotropic mixtures. So what are those two types? Let us see. They are minimum boiling azeotropes and maximum boiling azeotropes. Okay. So a minimum boiling azeotrope means what? It will be having lesser boiling point. Okay. Lesser boiling point in the sense what? It is easily going into the vapor phase. So which solutions will easily go into the vapor phase? The solutions which exhibit positive deviation, they behave as minimum boiling azeotropes. Okay, I hope you have understood it. Okay, minimum boiling azeotropes, they exhibit positive deviation. Okay, positive deviation in the sense what? They are easily going into the vapor phase. Okay, that means the interactions between the solute and solvent is less. Because the interaction is less, they are going into the vapor phase easily. And because they are going into the vapor phase easily, their vapor pressures are more. Because the vapor pressure is more, we say that it is a positive deviation. Okay, example of a positive deviation azeotrope or minimum boiling azeotrope is ethanol water mixture. Okay, Why is this ethanol water mixture we are getting? Because of the fermentation of sugars. Okay, one of the method to produce ethanol is fermentation of sugars. Okay, so whenever we are carrying out this fermentation process, whatever the ethanol we are getting only up to 95% of pure. Okay, remaining 5% is because of water. Here we are seeing the positive deviation. So it is a minimum boiling azeotrope. Next, coming to the maximum boiling azeotrope. Maximum boiling azeotrope means what? We have to heat it to a very large temperatures. Okay. Why do we need to boil it at a very large temperatures? Because the interactions are much. Because the interactions are much big. Okay. When the interactions between the solute and solvent is more, it exhibits a negative deviation. Okay. So an example of a maximum boiling azeotrope is nitric acid and water. Okay. So this is the diagram which shows about the fractional distillation tanks, and this is pertaining to the azeotropic mixtures. Okay. Next, colligative properties we would be discussing in the tomorrow's class. Okay. So today what did we discuss? We have discussed about the Raoult's law. Okay. And ideal and non-ideal solutions. What is the reason of non-ideal solutions? Okay. Types of non-ideal solutions, that is positive deviation and negative deviations. As well, we have discussed the azeotropic mixtures. Okay. So these are all very, very important. Please go through the textbook. Okay. I'll just start about colligative properties. Okay. So colligative properties, these are nothing but the properties which depend upon the number of particles in the solution. Okay. Rather than the nature of the particles of the solute. So see here, colligative properties are those properties of solutions that depend on the ratio of number of solute particles to the number of solvent molecules, and not on the nature of chemical species present. Okay. So in simple, we can say that colligative properties are those which depend upon the number of particles present in the solution. Okay. So we are having 4 important colligative properties. Okay. Those are nothing but relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. Okay. And what is the use of these properties means? By using these properties, okay, we can find out the molecular weights. Okay. As well as elevation in boiling point, we are saying. Elevation in the boiling point means what? When we boil a substance, okay, we can go for faster cooking and all that. You might have noticed people saying that if we add salt, what happens? The boiling point will increase. It takes more time to cook. That means temperature. We are increasing the boiling point. Okay. Depression of freezing point. So where are we applying this is? In the cold countries. Okay. During winters, what happens is the temperatures, they fall even to the single digits. Okay. So when the temperatures are falling to the single digits, what happens is there is more chance for the liquids to become the solids. That means they're freezing. Liquid becoming a solid is called as freezing, right? So the fuel like petrol, whatever that is present in the engines, right? So that also tends to freeze in order to prevent that, what do? Is we add some solutes to that. For example, ethylene glycol that is added to the fuel in order to prevent it from freezing. So these are the colligative properties. So let us see here, relative lowering of vapor pressure. So what is relative lowering? Relative lowering is nothing but it is the difference in the vapor pressure, okay, of the pure solute and the, sorry, it is the difference in the vapor pressure of the pure solvent and the solution. Okay, so see here in this formula, P naught, you're seeing this. So what are these P naught 1 and P1? P naught 1 is the vapor pressure of pure solvent. Okay, P1 is the vapor pressure of the solution. Okay, so whenever we are making the